Now that we've discussed Pascal's triangle, let's work on the expansion of x plus y to the n. And I want to start, there's already some text on this slide, but I want to start from nothing. I want to show you why we're doing all of this. You have, prior to this course, at some point been asked to evaluate x plus y squared. It's certain that you've been asked that before because we had to talk about the distributive property. And so, you wrote out x plus y times x plus y. You probably drew some little rainbows like this to distribute. You ended up with x squared and then an xy term and another xy term like this. Notice I didn't write yx, I wrote xy, but it would have been equivalent if I had. And then you grouped the like terms to end up with this. So you did all that work to get here. Okay. Now, I'm going to take for granted that you know right away that x plus y to the 0 is just 1 because anything to the 0 makes 1. And I take for granted that you're okay that x plus y to the 1 is just x plus y because something raised to the power of 1 is just itself. But how would you determine x plus y to the power of 3? Well, that does mean x plus y times x plus y times x plus y. But since we've already determined that x plus y times x plus y gives us this expression, let's jump ahead to there. So we'd have x plus y times x squared plus 2xy plus y squared. And then we would start distributing into this next bracket like this and like this. And we would end up with 6 terms. The first of which would be x times x squared, right? This one here, so that makes x cubed. Then x times 2xy, which would be 2x squared y. And then we'd have x times y squared, and then now we're onto these rainbows. Then we'd have y times x squared, so that's another x squared y term, and then the y times the 2xy, oh my goodness. And then we get this, okay? We group our like terms, specifically that these two do go together, and that these two go together, and finally we end up with this. Okay, now why did I do all that? I did all that to show you that it's a lot of work. It takes some time. Now, imagine if I asked you to write out x plus y to the 5 or x plus y to the 9. Oh my goodness, how many rainbows are we going to draw, right? It's just going to be too much work. So we need to find a way to get to the expansion of x plus y to the 9 or whatever value without having to do all of that work. And so that's where this binomial theorem comes in, will help us. Okay, so that's why we're doing this. So now let's jump back in and see what we can do. Okay, so the first thing we want to do is stop looking at just one row in isolation, and we want to start looking at the entire pattern that emerges as we move down the rows. The first thing we're going to notice, or the first thing we're going to talk about, are the coefficients. The coefficients are 1 in the first row, and then in the second row, we have 1 and 1. In the third row, we have 1, 2, 1. In the next row, we have 1, 3, 3, 1. These are the numbers we just saw in Pascal's triangle in our previous slide. So what would this be in the row of x plus y to the 4? Well, because we have the row above it, let's go ahead and add up those values. So the 1 and the 3 add to a 4, the 3 and a 3 add to a 6, the 3 and a 1 add to a 4, and then finally we just have the 1s. Now, it's important that I had things, written very clearly and well aligned to get those values, because of course you wouldn't want to put the 6 in this position or a 4 in this position because you'd not lined up your work well. But ignoring that, the values add up. We can use a program like Wolfram Alpha to check this without doing it out by hand. But just so you know, if we had multiplied our x plus y squared term, which gives us this either by itself or by x plus y twice, we would end up with this next row. So you can trust me on this one if you don't want to go to Wolfram Alpha. So now let's move into our next row, the one that is x plus y to the 5. What are the coefficients going to be? Well, again, we're going to add up those values, the 1, the 4, 4, and 6. But we want to start going back to the other work that we had done soon, which is recognizing that these are n choose r values, right? So when our n value, which in this case is 5, shows up there, it's also going to help us determine the coefficients. Like this coefficient is going to be 5 choose 0, and this next one's going to be 5 choose 1, and then here you have 5 choose 2, and that's going to work its way across the row. Okay, so we've got all those values sitting there waiting to help us. All right. The next thing we want to talk about, now that we've got the coefficients in place, is how we put our exponents on x and y. So if we look from left to right in this row of x plus y to the 5, you've got this factor of x in the first term, this factor of x, now I mean like this power of x as a factor within the term, and then this, and then what would come next? Okay, so x to the 5, x to the 4, x to the 3. You probably won't be very surprised. Your next one is x to the 2, and then x to the 1. And then the absence of x in the last term is the same as saying that it's x to the 0, right? Because x to the 0 is just 1. At the same time, our y values are going up by 1 in terms of the exponent. So in our first term, we don't have a y value, or we don't have a factor of y, and then we go y to the 1, y to the 2, and no big surprise, y to the 3, y to the 4, and y to the 5. Okay. An easy way to check that we've got them labeled properly, my n value is 5 here. So in the first term I had x was 5 and y was 0. Let me just erase so you can see it. I had x5 and y0. In the next term, I had x4 and y1, then x3 and y2, so I'm here now, then x2 and y3. And what we see is in each case, these add up to that n value, don't they? They add up to that 5. Okay, so if I had to do the next one, I know that it would go x to the 6, and then x5, x4, x3, x2, x1. At the same time, it go y to the 0, then y1, y2, y3 to y to the 4. So they always add up to the 6, or whatever the number is, the n value is. The next bullet asks us not to write out the row, but simply to predict the number of terms that will be in it. Okay. This goes back to something I talked about earlier. The number of terms in the row is different if I tell you the row number versus telling you what the binomial was. And the reason is this exponent, this 6 in this case, is our n value. N is 6. But that's not the same as the row number. So let's have a look. When n is 0, there is one term. That's the first row. Let me say that again. N is 0, row number is 1. Right? And there's one term. When n is 1, we are in the second row. There are 2 terms. When n is 2, we are in the third row. There are 3 terms. So we see here the one that had n is 5, we had 1, 2, 3, 4, 5, 6 terms. So we notice that the number of terms is equivalent to the row number, but that it is 1 more than the n value. So 1 more than the n value. So x plus y to the 6 is n equals 6, so we have 7 terms in that expansion. And x plus y to the 12, n is 12, so we have 13 terms in its expansion. This is something that is asked of us a lot, right? Because it shows that we're able to do work without doing the work, or we're able to, know something about the result without doing all the work. So it is an important recognition, an important part of this pattern to recognize that. Okay, so now let's again talk about x plus y to the 12. without doing all the work of x plus y times x plus y times x plus y, 12 of those, what would be the first three coefficients in our expansion? Okay, so this is going back to our Pascal's triangle work. So we have an n value of 12. All right, so that's what our lower subscript is going to be. And the first three terms are going to count from r values of 0 up to 2, I guess, right? So our first three terms up to 0. So let's observe how this works. Let's observe how this works in the row where n was 5, right? So we had our coefficients of 5, choose 0, 5, choose 1, 5, choose 2, and so on. So if we do that again here, let's just showing this symmetry of it. If we do that again, when we have an n value of 12, then we're going to count from 0, 1, and 2. And those we can evaluate in our calculator if we need the numeric values. Here we'll just leave them as 12, choose 0, 1, and 2. Okay, here's an expression we're going to fill in, or fill in the blanks we're going to complete together. In the expansion of x plus y to the n, there are how many terms? All right, so remember, when we had n of 6, we had 7 terms. When we had n of 12, we had 13 terms. So in general, when our power is n, we have one more than that for terms. So we have n plus 1 terms. The sum of the exponents for each term is what? Well, remember here we had 5, we had 4 plus 1, we had 3 plus 2, we had 2 plus 3. The exponents always added back to that n value. As we look at the exponents on x, they go from what to what? The first one started at the n value, and in the last term we had x to the 0, right? We didn't have 1, so they go from n down to 0. And at the same time, the exponents of y do the opposite. They start at 0 because we don't have a y here, and they work their way up to the n value. The combination expressions for the first three coefficients in the expansion of x plus y to the n, so there's our, it sounds silly to say there's our n value, there's our left subscript value, would just be n, and then we're choosing 0, 1, and 2. And the very last term would be n choose n. That's not the actual term, that's just the coefficient of the term, right? So that's how we use Pascal's triangle to know the coefficients without having to do a lot of work in the expansion. All right. In this expansion of x plus y to the n, for the exponent of y, when the exponent of y, sorry, let's say when, my apologies. When the exponent of y is 0, the term number is, that's a little bit of bad grammar, but the term number is what? Okay, in the expansion of x plus y to n, the exponent of y is 0. Well, that was what happened in our very first term, right? That first term. We're not gonna talk a lot about the term number within the row and the row number all at the same time, because it can start getting a little bit heavy. But of course, I want you to remember that we always start at the first term. Like, that might sound so obvious that it's not worth saying, but it really is. There's no such thing as a 0th term or 0th row. And I bring it up because that's going to matter in a minute when we're driving our formula. So the first term is when y is 0. When the exponent on y goes to 1, right here, we're at the second term. When the exponent of y goes to 2, we're at the third term. We're bringing this up to show that once we get to the last one here, like y to the 5, let's say, the exponent of k is 5 on the 6th term. So the exponent of y is k on the k plus 1th term. Okay, so let me say that again. The k plus 1th term. I know this is a lot right now. You're like, why are we doing this? It's going to come back in a second. Okay, so let me say it one more time. If we talk about the exponent of y. So let me pull out the y. This was y to the 0. This was y to the 1. This was y to the 2, right? Up to y to the 5. It was 0 on term 1. It was 1 on term 2. It got to 5 on term 6. So if this is k, this is k plus 1. That's what we're trying to get you to see. We're going to be talking about a k plus 1th term pretty soon. So exponent of y is equal to 1 less than the term number. All right, we're going to take all of these patterns, we're going to build a formula, we're going to talk about the expansion of binomials. I hope that later when you go back and watch this, you're going to say, oh yeah, all this stuff is super obvious. But I know right now it's weird sometimes to talk about the patterns that emerge in this work when you haven't necessarily done a lot of this work. So again, you should feel very comfortable to the point of memorization of what those first 3 binomials expand to give. But I'm sure you're saying, I don't really do these much. Why would I do all this work? Well, all the work we're doing is so that you don't have to spend all your time drawing rainbows to multiply out binomials. I'll see you at the next slide.